So hi, my name is Timothee Cour. I'm very happy to be here today talking to you. The title of the talk is Movie Script, Alignment and Parsing of Video and Text Transcription. This is joint work with my advisor, Ben Taskar. And I've worked on other projects, but I thought this one was most closely related to Google. So this is the type of applications we're interested in. We'd like to have automatic collection of annotated actions in the wild for retrieval and indexing purposes, also video and image retrieval, and video browsing and summarization. In the longer term, maybe also video mashup, where a user would have a database of segmented and indexed videos of objects, and he could plug them and mash them together. For example, here, Shannon walks away from side would be able to plug those different pieces together. So we're going to use, instead of image datasets, we're going to use movies and TV series. So those are not just arbitrary videos, but they are very structured. And the first part of the talk, I'll talk about scene-level parsing, where you take a video and some text data, and the output is aligned and segmented shot boundaries and scene boundaries aligned with a screenplay. The second part of the talk, I will show retrieval of actions, where you can query for actions from the database of videos, and also segment out and recognize and name characters. And if I'll have time, I'll talk about finer grain segmentation and alignment using shape. So first part, scene-level parsing. So I'll let you read this code. So here's a simplified version of how you construct a movie scene. You start from the storyboard. You take some actors. Oops. You find different camera positions, and then establishing shot. You have a close-ups, over the shoulder. So those are the typical shots, and also shot and reaction shot, typical of dialogues. And then the goal of the director is to splice up together different viewpoints to have a continuous scene. So what we're going to do now is do the video deconstruction. So we're going to reverse the pipeline. We're going to find the shot boundaries. That's an easy problem. We're going to then find the scene boundaries. And then we're going to find recover the initial string of shot sequences taken from a single camera viewpoint to recover smoothly continuing shots. So there's a lot of previous work. Most of all have dealt without any alignment with screenplay. So in our work, we're going to use the screenplay data, which is widely available for a lot of videos. Let's look at what it's composed of. You have dialogues. You have narrations. Scene transition labels. That's the one we're going to use for alignment. And so we're going to try to align it with the frames of a video. So ideally, we would like to align each shot to a particular dialogue or narration element. Here, what we're going to do is extract the scene transitions and extract the scenes and align them to the videos. However, as you notice, there's no temporal alignment in the screenplay, so we're also going to use additional information of closed captions, which are embedded as ASCII in the DVD. So for the alignment, we're going to use the text of the dialogues. Only the text is transcribed in the closed captions to align it using a simple dynamic programming. It's called dynamic term warping here, alignment between the dialogues in screenplay to the dialogues in the closed captions. Notice that we don't have any temporal alignment for the other parts, which are scene boundaries, which we're interested in, and the narrations, which are interested in for extracting actions. So this is very imprecise, and it's actually a hard problem because, again, unlike dialogues, narrations are not temporally aligned, and also locally, there's no difference between a shot boundary and a scene boundaries. So question, is this a scene break? So the answer is no, because as we can see, it's alternation of different shots from the same dialogue. Now, is this a scene break? So the answer is yes, this time, because we transition from one continuity of people and locale, which is two agentic people, to another locale, which is two other people. And it's particularly hard in this case because it's a smoothly continuing shot between the two, that transitions between the two scenes. So unlike shot boundaries, scene boundaries cannot be detected purely locally. So our approach is going to simultaneously group the shots into scenes mentioned in the screenplay and find a reordering of the shots such that we recover as smooth as possible transitions in the camera position. And this is unlike clustering approaches because we also want to have as smoothly varying shots as possible. For example, in this sequence here, you can see that the camera smoothly varies from a close-up to a far shot, and then to a different person, where we have also recovered the frame registration, camera registration. And clustering approaches would not have such a property, and it's also hard to determine exactly the number of clusters here. So we're going to build a generative model a simplified generative model for generating a movie. Start by generating the scene boundaries given the screenplay. Next, you generate the scene structure, which is generating a parent shot for each shot in the scene. And this defines a Markov chain from which we can sample each shot independently. So generate the first shot in the scene, then the second shot, third shot, and the last shot. Again, modulo this reordering. Finally, we're going to generate the frames inside each shot. So we introduce the variable probability of a scene boundary, probability of a parent of a shot given the scene boundaries, and probability, this is the appearance model, probability of a shot given its parent. So this is our graphical representation, where again you have on top the scene boundaries, and then you have the Markov chain given the scene boundaries, and finally the shot appearance model to generate each shot. So our appearance model is very simple. You take two shots, and you're going to say that they're compatible only based on the last shot on the last frame in the previous shot and the first frame in the next shot. So we want them to be similar. Here, this is low because the second person here is very different from the first person here. And notice this is asymmetric by definition of the first and last frame. On the opposite, this is high because those two are similar, say, in color space. So we're defining, in the end, non-symmetric and probability transition metrics. So let's look at the first simple case where there's no scene breaks. And if you do inference in the model, you want to find the maximum likelihood probability of parent shots. This amounts to a traveling salesman problem in the sequence of shots. And of course, this is a very hard problem. And so we haven't solved it yet. But we're going to use a simplified model where you'd use memory-limited TSP, which is you're only allowed to jump back and forth from a limited amount of shots. And so, for example, here, with a width equals to 2, the first one is OK. The second one is not because we're jumping back 2 shots as opposed to 1 shot. We're using much larger K in practice. So properties of this limited memory reorderings is that permutation we find is close to identity. Also, the similarity of shots is sparse, which is good for our purposes if we want to define more complex shot transition matrices. So Bellas has proposed a linear time dynamic programming solution for the TSP limited memory problem, where the state space is the set of cities you've visited, set of shots or cities you've visited up to time t, and the current city you're currently visiting. So So the dynamic programming solution, which actually would also hold with without limited memory, but it would explode, would be to minimize over the previous shot in the sequence of the cost up to that previous time, plus the cost for jumping from the previous city to the current city, Wi prime. And so notice that even though this set exponential notation is exponential, in fact, it has the number of such sets is actually exponential in the width of the reordering, but it's linear in the number of shots. And so we can build a dynamic programming table compactly, again, where we transition from a state of a previous shots and a previous set of shots to the next shot. And the computation time is linear in n. Again, example. So we have the current city at time t. So we've already seen all the green checks, and we want to visit all the other ones. So we're at city at 3, and we cannot go too far in the gray shaded areas. And so next step, we can transition to this state, visiting this city here, and you see the transitions updated as follows. So now let's go back to our initial problem, which was you have to jointly segment into scenes and also to find the shot reorderings. So this amounts to doing this for every single interval, finding the shot best permutation for each interval. So the naive algorithm would be compute a TSP for each of the and choose 2 possible intervals, and then combine using dynamic programming. It's tractable, but it's very expensive. So we're going to do a joint dynamic program over the scene labels and the shot reorderings. And we can see that we're going to gain a factor n by including the state space, also the scene label. Back to our example, where it is city 3. Now, we can choose arbitrarily to switch to a different scene. So we were at the beach, and we're going to transition to the jungle here. And we're going to pay no penalty in the transition, which means that there is no expected similarity between shots from 2 different scenes. And so the transition is updated as follows. Okay, so let's look at some results now. This is the data we've played with. So 60 TV episodes, 5 movies, 600 screenplays. So it's more than the movies we had. So it's a large number of images and a large number of words. So some results. So one typical episode, for example, of Lost would be to have 60 scenes, about 600 shots, 60,000 frames, and 300 dialogues, which are individual elements, and also you have all the other rest narrations, which we are interested in for actions in the second part. So this is shot detection. That's an easy problem. We get 97% precision F-score for precision recall of shot boundary detection. The more interesting stuff is the scene segmentation with alignment. So what this table shows here is that the width of the reordering helps a lot. So we go from a width of k equals 1 to k equals 12, and we're plotting here the accuracy for predicting a scene label of a shot, for example, at the beach or in the jungle, and also the score for scene boundary detection, regardless of the shot label, the scene label. And those numbers, again, are monotonically increasing for larger width. Also, now if you look at the second row, this is the uniform model where we don't have any bias from the screenplay as to the scene labels, the scene breaks. Okay, the first one was using the screenplay to find, to bias where the scene breaks should be. We have large incertitude, but it's still useful bias. And the second one is without it. And we can see we have considerable improvements with using screenplay. This is going to be very useful for action retrieval. Of course, time increases, but it's not too bad. It's about 1 minute in the most complete model.
What are you using from the screenplay here to bias the alignment?
So let's see if I could There was those scene labels. If you notice, there was in brackets exterior at the beach, interior in the jungle, and those kind of things. There's about a little more than the actual number of.
So how do you use those?
So those are the available scene breaks for finding scene alignments. And we're going to use, from the dynamic time warping algorithm where we align dialogues, we're going to say that this scene break can wiggle anywhere between those, the last timestamp and the next timestamp. And this interval will be pretty large.
So you're using timestamps that you get from aligning dialogue as the...
From aligning dialogues to closed captions, yeah. Mm-hmm. That's what we're using. So some results on the shot threading, shot reordering. So we evaluated against ground truth on one episode of Lost and one episode of CSI, and we get an accuracy for predicting the parent shot of about 75%. And so as you can see here, well, with some more example, but this is before reordering.
What does a parent shot mean?
Parent shot is in the generating sequence. What's the shot that generates you? Another way to view it is the previous shot in the permutation of shots in a given scene. That's the parent shot. So this video is again before threading, so it keeps changing viewpoints. This one is much more smooth. This is after threading, so we see there's much less breaks in camera. Again, a few more examples. Again, this shows the advantage of, as opposed to do clustering, doing reordering, because we have smoothly varying camera position from a close-up far off to even far off, and then transition to a different person. So I have a lot of examples of those. I'm going to skip it. Maybe this is more easily seen. So we have...
You can hand label 60 of these shows to start with, so you have some prep data.
Yeah, so we hand labeled about half of the scenes for 2 episodes, one of Lost, one of CSI. That's how we got our 75% accuracy, and then we're also going to show results for scene segmentation. So again, this is viewed column-wise, the last frame and the next frame in the shots. A harder scene, more interesting scene without just a dialogue. Okay, finally, so we have those results for all the 20 episodes of Lost and CSI we tried on. This kind of alignment results. So this is the narration. This is the aligned and reordered sequence of shots, where again you have for each red thing here, this shows where the scene breaks are, and also it tells you what's the set of characters you should expect to see in the scene. That's again parsing the screenplay. So this is useful for browsing summarization. So. Okay, so far we were just looking at the level of scenes. We're not going inside the shots or inside the frame. So we're going to try to see what we can do now with the actions, and if we can retrieve actions based on the visual appearance of people, track faces, and segment them. So this is more towards retrieval and indexing. So we have a database of movies, and we have some queries, like points, opens the door. Can replay it once more. Oops, too bad. So we collected statistics here from 24 screenplays, again, downloadable from the intranet of Lost. And let's see some interesting data we can obtain. So this is a screenplay. We parse it. This is using simple grammatical rules into scene transitions, narrations, speaker and dialogues, and then we do sentence tokenizer and powder speech tagging to extract, say, the verbs, and we also actually do parsing of the sentence to obtain subject-verb complement. And finally, we're going to semantically filter using WordNet dolls as instances into like 20 categories. We have verbs, actors, objects, and locales. Let's look at a few of them. So there's like 25,000 instances of verbs with like 2,000 different kind of verbs. Looks is the most common. So any verbs like looks, stares, glances, this is going to be the most common type of words. Then you have motion verbs, like runs, walks. Those are fairly common. Those are more interesting verbs because we don't have such existing categories of databases for it. So those would be the ones, or would be mostly interested in, for example, climbs, bunches, cases, and so on.
I assume that your queries are one word and one of these words.
So it could be compound, like open door, or.
So what's this set of queries?
So we're using WordNet. We have categorized 20 different semantic categories. Those are verbs. There's our actors, objects, instruments. So you can arbitrarily define your categories, and then your query could be.
Taking these from the screenplays. Right?
Yeah, those are taken from the screenplay, but the parse screenplay, not just the raw data. Okay, so interesting also scene locales, like we can have queries for beach, jungle, site, those kind of interesting queries for a user. And also time of day queries. Also scene keywords like interior, exterior, these are very, very common. Black, overlap sound, off screen. Okay, so now we're gonna try to align at the finer level the text screenplay that is parsed and the videos. So given the screenplay, we're gonna do pronoun resolution. Why are we doing this? Because in the screenplay, first of all, the interesting bits are not the dialogues, because they don't convey any information about the visual scene. The interesting bits are the narrations, but about more than half of them contain pronouns. And so we need to resolve them in order to align them somehow with people. So in this example, the pronoun resolution, and Said holds the empty bottle in his hand becomes Said's, and her becomes son, given the context. And next, we're using verb frames. Again, that's going to be useful for the verb queries. Said holds bottle, and Said questions son. This is the parsing of the initial screenplay narration. Then we would like to identify people, locations, objects, and actions. So pronoun resolution, I'm going to skip this. This is adapted from Hobbes' algorithm, but in our case, it works very well because the sequence of text is very, very structured. And so we can, with high accuracy, about 80%, recover the pronouns for the dialogues, for the narrations only. So now we can use this to, at a slightly finer level, not yet at the pixel level, but at least at the frame level, align and query for different action verbs. So this is using the aligned screenplay, the aligned shot boundaries, the aligned scene boundaries with the screenplay to query for different kind of verbs. For example, okay, shouting. Look at. Whoops. All right, you can look at focus on one and see that it's more or less focused on one type of action. And we have this we have tons of instances of each actions. Okay. Fortunately, it's a bit dark. So now we'd like to improve the retrieval in order to go to the pixel level and to the to have face track and naming. So this is more involved, but it would help us to have more precisely aligned actions in terms of width, temporal width, and also spatial width. So we want to do face detection, tracking across shots, also character naming and segmentation. And aside, for later, we'd like to do camera pose registration, core scene geometry, and gaze estimation. We're not going to talk about this here. So I'll let you read this quote from Hitchcock. Okay, so people are central in movies. Anything we want to do with actions is going to have to pass through people, and in particular, face recognition. So we're going to take Hitchcock's advice and find those ovals, those orange ovals in the scenes, so that to do face tracking across different pose variations in order to have smooth tracks. So you use Viola Jones' as a frontal detection, which is low recall, but somewhat high precision. Then we build some discriminative color model. This is very simple. Here we're simply using the frequency count of a given color inside of the bounding box divided by the frequency count in the neighborhood outside. And so we're using this to track the face by trying to fit some shape of the face in the subsequent frames to fit this color scoring. Again, notice the face can turn, rotate, so we would like to have a lot of variations. In practice, we're actually going to use tons of different deformations of the face across scale, translation, aspect ratio, and also shape, whether it's frontal or profile. So to this is going to heavily rely on finding convolutions. I'm going to let you watch some long face tracks. So again, there's like, at some point you're going to notice weird shapes. This is, oops, I don't know why it stopped. So those weird shapes are the non-frontal ones, the profile ones. Okay, etc. Notice again, VillageOnes is going to miss a lot of those face tracks because of non-frontalness and just in general because there's no tracking involved. So notice these examples here where this is very dark and we're still able to recover the face track. This is because we have a discriminative color model here. And we can recover after the occlusions from, like, say, the fire. Okay, so this heavily relies on convolution. So we're going to propose very fast convolution with so-called polygonal approximation. So it's relying on only 3 ideas. First of all, it's Green's theorem. So we want to compute a convolution. This is, again, our face shape. And on the template, which is, it's inverted here, on the template, which is the Cour color model. And Green's theorem tells you that you can compute a surface integral as a line integral, which is sparse. So this is good. Next, we're going to use a polygonal approximation of the contour of the object. And we're going to show how to compute this efficiently and optimally in using dynamic programming. Finally, we're going to combine this with an extension of VillageOnes to 45-degree integral images in order to compute those integrals not over the initial contour, but over the polygon approximated contour. And so this is going to be very fast convolution in order of number of vertices in the polygon, as opposed to.
So to make some assumptions to make the step number 1 go, right? Because you have to assume something about the smoothness of the function, right?
So here we're using discretized pixels. So there's no such smoothness, but however, you could consider other type of. So this works completely with arbitrary topologies of the mask. It could work with holes, multiple components. However, if it has multiple color, then you need to encode each one color separately. Okay. So the first part is Green's theorem again. You all know this. I'm going to skip it. Now the interesting bit is the polygonal approximation. So we have a shape that we want to approximate, say, with 20 vertices. Sorry, how much time do I have? 25 minutes before the questions? Or including the question? Okay. So what we're going to do is minimize the approximation error between the initial shape and the shape obtained with the polygonal vertices. Okay. So the approximation error between the shape and the vertices is the sum of the areas here. Of course, it could go inside. This is for display purposes. And so we're going to approximate this sum of errors by those shaded here. So it's just what we're doing is skipping the corner bits, which are small compared to the rest of the areas. So this is going to be positive. Sum that we're missing, if it goes inside, it's going to be a negative sum. So those are small in practice. So the dynamic programming solution now is you're defining the error up to vertex m of a vertex zm as the minimum over all the previous other vertices of the approximation score. Okay, and so you can use dynamic programming here. You can use reuse overlapping computations by minimizing over only the previous vertex of the energy so far, plus the energy on the last added vertex, so the last segment. And so we're going to build this table of number of discretized positions where you could fit the vertices. Notice we're not constraining to be having a vertex on the shape, which would result in really bad approximations. And so we're going to build this dynamic programming table over number of vertex positions times number of vertices, say 20 in our example. So the complexity here is number of vertices times number of positions squared, because of the dynamic programming, times number of times the complexity of each cell here, the computation of the last segment. However, notice that the previous vertex and the next vertex have to be aligned in either 45-degree angle or along straight lines. Okay, so this is the key part where we're going to reduce complexity into a number of vertices times number of segments instead of number of squared positions. So this is much smaller. Finally, we can show that the computation per cell is constant time as opposed to something complex. So the key here is to notice that we can compute the error on the given the previous vertex, compute the error on the given the previous vertex z2. We can compute the error by having a z3 in constant time by having a bunch of pre-computations. First of all, we pre-compute the projections. That's using simple distance transform to compute projections of any vertex. Second, we're going to approximate the distance between this, the sum of the scores here, to the segment. We're going to approximate it to the distances of the points here to the line as opposed to the segments. So this is, in most cases, a good approximation. Finally, the sum, we're simply using cascading operation to compute the sum of the vertices. This is classical, can be computed as a difference of two integrals. And so in the end, final term can be computed in order constant. And we have very efficient ways to compute the approximations. This is an example that shows you that polygonal approximation depends on the rotation, but not on the scale. So for each rotation, we're going to have to recompute it. But that's fine because this is pre-computed prior. So we're doing this for faces and for other objects. Yeah, lastly is the combination of this with the Green's theorem. So in order, we're going to sum over not just the, we're going to sum over segments as opposed to summing over individual pixels on the boundary. And this is simple extension of Villa-Jones integral image to 45 degrees angles. So in the end, what matters is the computation times goes to 2 times the number of vertices, as opposed to Villa-Jones, which is 1 time the number of vertices, which is 4. So that's same order. So we have huge storage size improvements. For example, 200 by 200 template with efficient encoding can be stored as 20 bytes with the polygonal approximation, as opposed to 40 kilobytes if you use the binary image to store the mask. So this is factor 10,000 improvement. And also the computation time improvement is also very big. So if you use n log n with convolution, can go down to n times number of vertices in your polygon with the polygonal approximation. And it can also go down to linear with coarse to fine on top of it. Coarse to fine, again, is valid because we can have random access computation of the dot products, as opposed to FFT, which is global, so you can do coarse to fine. Yeah?
You're doing this individually for every frame?
What is that?
You are solving this individually for every frame?
Of the video, yeah.
Without any temporal continuity?
Oh, so yeah, in practice we actually do have temporal continuity. This is mostly for avoiding to launch onto a new track. Suppose there's 2 faces. but computation time would still be completely doable if you did over a neighborhood. Or
would it be valid to assume that your current track would be with some delta error of the previous track?
yeah, so we're doing this. We're only considering a small rectangle to compute the next track and also some smooth variations across scale. Yeah, good question. So now we also want to do segmentation. So I'm gonna go quickly over this. The idea is we want to fit those ellipsoids to find tracks and segments. So this shows also naming. So we have a dialogue here between two people, and again, notice to compute the naming here, what we're going to do is use the reordering of a sequence of threads and into a consistent sequence, and use a simple voting scheme to vote for each thread. Vote based on the co-occurrence of dialogues between the name of the speaker and the given shot that is shown. So this is a very core scheme, but it works okay because we have a larger scope to compute the voting scheme as opposed to something we'll see later, which is shot per shot. So another video. Whoops. Another video, another dialogue scene. So it's not perfect, of course. Segmentation is not perfect. Okay. Last video. Again, the longer the scene is, the longer you can have redundant information to compute the bias for being that character or this character. And finally, this shows the advantage of using shot reordering as opposed to do it shot per shot. So on the right-hand side, you see the exact same scheme applied to a shot per shot voting based on the co-occurrence with dialogues. So on the right-hand side, again, makes a lot of mistakes because the voting is small and there's a lot of incertitude in the alignments. Again, so there's a lot of previous work on finding faces, especially in Joseph Sherman's group, and Deva Ramanan. I've worked on extracting faces. They have pretty impressive results also for face extraction. For example, Deva has extracted 600,000 faces. We're going to skip camera pose registration. Just some results where we register pose frames from the previous shot to frames in the next shot. Okay, maybe I should stop here in like 1 or 2 slides. I'm going to skip the. How much time do I have?
We have 15 minutes.
Okay, so maybe I'll skip this part and go to the questions. Just some results on. So articulated, we're having more articulated templates and segmentation with articulated templates. So that we want to do again for videos using this efficient scheme and this efficient template matching. Oops. So other results where we compute not only the segmentation of this is on Weisman horse dataset, not only the segmentation of horses into different parts, but also the labeling of different parts of the horses. All right, so in conclusion, we extracted, there's a lot of structure in movies and TV series, more than in arbitrary and constrained videos. And the structure can be recovered and to improve tracking, labeling, and segmentation. So we propose a way to recover continuity for tracking through this threading using dynamic programming. And finally, the alignment with the screenplay is crucial for having accurate indexing. It gives a cheap way to align a lot of data. But again, you need screenplay, and it's available for a lot of movies you could find on the internet. And also the closed captions, this is very easy to get. This is most DVDs produced in the US. There's tons more to do, but this is just the tip of the iceberg. Just very briefly, some other projects I've worked on. So linear time, multi-scale segmentation, some segmentation of large point cloud data. And on inference side, so I have designed spectral relaxation for solving Markov random fields for the map problem using eigenvectors with affine constraints, which encode site per site constraints. And we obtained a 1/number of labels approximation guarantee. And we extend this using an eigenvalue optimization for maximizing arbitrary general quadratic energy functions under affine constraints. And we can show that we have tighter than LP relaxations for mapper MF and tighter than spectral subgradient. We can talk about this if you're interested. OK, so this concludes my talk. If you have any questions.
On your articulated horse model, where do you get the model for the parts? Do you put that in, or is that derived from the data, or how does that work?
This is hand design, but this is again cheap to obtain. What we do is what we do is we obtain we have the horse segmentations from the Weisman horse dataset, and we just cut into different limbs. We just keep torso, head, front legs, back legs, and that's it. And then we simply have fiducial control point model to wiggle around the.
Have you been able to do that for other objects or other animals or whatever? Or is the horse the only one you've done so far?
This horse has been the one I've done so far. But yeah, we obtain like 94% precision for pixel-wise labeling accuracy, and 95 using the articulated model.
Have you done anything with soundtracks?
So we haven't done with soundtrack yet. This is also an interesting problem, especially because of the weak alignment between closed captions and the videos. It would seem it's very aligned, but it's actually not very well aligned. And so using soundtrack would definitely help. Apparently, gender discrimination is more or less easy, so that could help in a lot of cases. However, when there's background noise, it could be a little more complicated, but I believe with some work, it could definitely be a big improvement. Also, for YouTube videos, soundtracks might be the only way to go, since we don't have any screenplay available. So you might want to use this parsing of audio data.
Where do you get screenplays? Why are those available online? Are they published? Are they bootlegged? Or what?
Yeah, I haven't looked too much into the legal issues, but so far we just downloaded from websites. They're like publicly available for a lot of TV series, especially TV series. They are very structured, and for movies as well, you can download. Like, there's really a lot of such screenplays available.
For most movies, or just selected subset?
I wouldn't say most movies. I would say I've seen it for at least 1,000 or more movies. But I mean, this is a lot to start with. Yeah.
So if you can go back to your slide where you were doing the pronoun resolution and the word detection.
Yeah.
So once you have all of that, what's your actual representation model?
This one?
Yes.
So say that again.
So once you have those things where Shahid holds the bottle,
Yeah.
what's your representation model?
Okay, so we're simply parsing into loose grammatical categories such as subject, verb, and object. And those are slightly loose categories that we allow for reorderings. For example, Jack is helping, then helping would be the verb as opposed to is, which is not very informative. And object is, again loosely defined from the parse tree. We don't use a strict parse tree, we use something a little more informative so that we can later retrieve actions for this.
But then do you try to get a model for the bottle and
No.
resolve it later on?
No, we're not trying to build any models of objects at this point. This allows us again to use much larger classes of classes of verbs without knowing anything about it. This is purely for again line retrieval, so informed retrieval, as opposed to detection. But again, that would be based on this large data set that we could collect, then we could start building models.
So I can think of a bunch of filmic techniques like shaky cam or smash cuts or things that might cause you trouble. Have you had enough, have the television shows and movies that you've tried been enough that you can spot specific problems or troublesome directors?
So there is, for shot boundaries, we had some problems with the hardest part about, for example, shot detection was the smooth transitions, the fades. For those we have a simple fix, which is, for example, when the frame is uniform in color, then at some point you decide it's like a separate shot, black shot, and actually those black shots are also mentioned in the screenplay. For the shakes, that's going to be more a problem for whatever we do with tracking of faces. I mean, I've showed a couple of videos where camera has fast motion, but there was no such thing as shake, like in amateur videos or stylish videos. This is a harder problem, yes.
If you don't use the constraints from the dialogue, what kind of performance do you get in scene boundary detection?
So I had numbers for this.
Was your uniform line?
Yeah, that was a uniform model. So the line model was on the top, and the uniform model is on the bottom. And so
uniform is without using the screenplay.
Yeah, uniform only uses the appearance model, and obviously you're going to do very, very badly at the scene labeling, because if you shift from one, you're dead. So that's not very important. But the interesting bit is predicting the scene boundaries, so that we still do better at that here.
And you dropped the last one off just because it was going down at that point?
Uniform. Yeah, I guess it was just doing very bad. Yeah.
Yeah.